as they panic about. Hey bro, let's big cheese. That's all the statement I needed. Indeed, let's big cheese. I'm actually going to need everybody's help on that one. I actually don't have a copy of the big cheese with me right now. I guess we might not big cheese. So here, let's just do this. What? No, give me that. Big cheese. Okay, I don't have a copy of big cheese on me, but we can big cheese. We'll figure it out or something. What cheese problem would you like? Or are you looking at? Or do you just need right-hand rules in general? I have to go out to my car. You gotta wait one diddy darn minute. What? Woof. For Z. Speaking of which, if he's out there, if he's found this, Sir Jacob of the Intergalactic, the big chi has been submitted. Okay, if you're my CP class and you're still sticking around, this is actually something we're gonna do later in the year, so this might be helpful if you just like don't leave just yet. You know this as multiplication, right? And then you learned this is multiplication, right? And then you learned this is multiplication, right? Turns out that your poor third grade teachers that taught you this isn't multiplication. This is special multiplication with vectors. And we haven't really seen this yet, but they left. Neat. If you wanted to understand how to multiply vectors, well, let's look at these two vectors here. We'll call this vector A, call this vector B. This is actually referred to as a cross product, whereas this is the dot product. Okay, so that's the idea of a dot product, cross product. What we're actually doing in a cross product is we're looking for how much of the vectors are perpendicular, and for the dot product, we're looking for how much of the vectors are parallel. Okay, what I mean by this is if we look at vector A, and we're going to see how to do this in a few days. Vector A, if we know what angle it is sitting at, using sine and cosine, we can break this up into some vector A in the x direction, and we can break this up into some vector A in the y direction. Okay? And if we actually see this vector y actually sits over here, and this is how the head-tail method goes, right? So we get sine and cosine to do that. What this means, though, is that the dot product is trying to multiply together only the x component of A to B, because they are now parallel. And the cross product is only trying to multiply the perpendicular component to B, because A, Y, and B are perpendicular. Which means that if you have something like A cross B, what you really have is the magnitude of A times the magnitude of B, which are absolute values, times the sine of theta. And for a dot product, you have A dot B, which equals AB magnitude times the cosine of theta, because the cosine gave you this and the sine gave you that. Okay? What this is really useful for is this kind of crazy idea. orthogonality. Take your hand and make the physics gang sign, okay? Basically, like, make a gun pointing forward and stick your middle finger out, so everything's at 90 degrees, okay? You see that? See how I'm doing that? It's like this. This is an X, Y, and Z axis, and basically, if I wanted to draw that, it would look, this is your normal, like, X, Y, but then there's Z, okay? So those are our three fingers there, X, Y, and Z, just like that. What this allows us to do is, if we pretend for a second that we take our fingers of our hand, and I'm going to draw the worst hand you've ever seen, but it'll be good enough. Thumb, and go 1, 2, 3, 4. Good enough. If you take your hand and you put it along the A vector, so let's say I have vector A cross B, okay? What would that equal? If this is my A vector here, you take your fingers and place it along the A vector. And what you're going to do is you are going to cross them to the B vector. So you're going to bring A to B. And when you do this with your hands, you're going to find that your thumb is sticking out in this direction. Okay? So these two vectors, A cross B, they're going to give you some new vector, C. We can honestly call this a resultant vector, believe it or not. And this vector here, C, is pointing, actually, in this case, it's pointing out of the page. If you're not out, you could be into the page. And we talk about Robin Hood a little bit later on in the class. Okay, we'll see that later on. It's not going to be too insane when we do it. Everybody who's ever done it has understood it, and there are a number of individuals that send me emails that are like, hey, I went to CMU and I'm teaching everybody how to do the right hand rule because I learned it in high school and these chumps didn't. So that's kind of nice. Okay. Miss McCarroll, you're looking at some of these questions. How many are there? Oh, someone needs to work on her camera skills. Camera skills! Woo! Okay, anyways. Let's look at this one. Which direction is B from wire 2 at wire 1? Okay, so this will be a fun one, right? I'm going to reorient this so that this looks correct. Okay. This is wire 2. This is wire 1. Nope, I have that backwards. This is I1. This is I2. Okay, from wire 2 at wire 1. So the way we do this is we put our thumb in the direction of the current. So I'm placing my thumb down in the direction of I2. And when I curl my thumb around to the left-hand side right here, my fingers are going to be the B field. So when I curl my fingers around, I actually see that my fingers are coming in on this side. So this is my inside and this is my outside. Oh, look, I made a face. Hee. And it's going to be in everywhere over here. So like it's in here, it's in here, it's in here from line 2. Wire 1 is going to cause something different to happen, but from wire 2, it's in on this side over here. Okay? So looking at this, it's not up or down because this is up and down. It can't be that. It can't be left or right. We're looking into the page here. Now, yeah, it's got to be into the page. It can't be left or right here because if we kind of take a look at this, it's actually only going left, so to speak, whenever it's not even in the plane of the wires anymore. If it's like you have 2 wires here, it would be going left out here like that. And that doesn't make any sense. Like we're going here to here, so you're back into the page. So that's that one. Does that kind of make sense for that one there, Kaylin? I hope so. If it doesn't, we can look back on it. But for these ones, whenever you have a line of current, thumb in the direction of the current, curl your fingers to make the B field, and then hit the page or pretend you're coming out of it. Okay. What I also like to do, Kaylin, is I like to place my pencil on the actual like current, and I like to stick my finger on the pencil. And then what you can do once your finger's on the pencil, you can actually like place the thumb on that pencil and wrap your fingers around it. And it makes more sense. You're going in on one side and your fingers are going out on the other, because you can kind of feel it a bit more with the pencil. So I like to just set it on the sheet of paper, put my fingers there, and then wrap them around to give me a better idea if I'm having trouble going in or out. Looking at this next one, number 4, a current carrying wire is placed in a magnetic field. Which direction is the force on the wire for segment B? Looking at my current, I'm going left and then down and then over. So my current is going down along this segment. Now, if we have a current carrying wire, the force acting on it is going to equal to I, which is the current, and then L cross B, the B field, with this L being the direction of the current. So what I can do here is, since I'm running a cross product for this, I need to go L cross B. In this case, my L is pointing down to follow the current down through B, and my B field is going to my left. So when I curl my fingers to that, my thumb ends up sticking into the page. I actually have into the page here. Okay? So your fingers go in the direction of the first vector. In this case, it's L, which is in the direction of I. That's going down. And then your fingers curl in the direction of the B field. And in that case, that's over. If I were to draw that, it would be like, this is my L vector going down. My B vector is going over like this. If I go L to B, I find that my force is pointing into the page. Okay, because I'm going L to B. Does that second one make sense? Oh, it hurt. It hurt. Kind of curious what the third one is. Okay, cool. We're good on the second one. For this one here, what direction is B above the wire? No, it's okay. Yeah, I know there's a big delay in the stream. I try to minimize it by modifying some settings, but it is what it is. Here, how about this? I'm gonna go make myself some chocolate milk, and you tell me what direction is B above the wire, because we're gonna have a delay anyways. And okay, so the derivations equation we learned for torids, will we ever do real equations with them? Kaylin, do problem number 8. Give me an answer to this. I have an answer. As to Olivia, derivations equations we learned for torids, will we ever do real equations with them? I assume you're referring to, as we wait on Kaylin for her answer in the chat, you're assuming that for the solenoid, the B field on the inside of a solenoid, oh geez, which way is this going? B field's going this way. B field on the inside of a solenoid is equal to mu naught I N, which is also mu naught I N over L. We didn't write it this way in class. And for a torrid, the equation was B equals mu naught I N 2 pi r, where r is this distance, with this being 0 and 0. It is out of the page. It is out of the page, Kaylin. It's out of the page because whenever you are actually above the wire, your fingers are coming out of the page. When you are in front of the wire, so you're in, if this is like my page here, when I'm like here, that's when my fingers are going down. Okay? So above it, you're coming out of the page. So good job on that. As for your question, Liv, with these two equations, will we ever do problems with the equations? For AP Physics 2, kind of. That's super vague, right? We're going to have a little bit of a mini lab where we play with solenoids, specifically trying to figure out what N is in a solenoid. We're also going to have a lab later on where, and we haven't gotten to this yet, we're going to use solenoids and drop magnets through them, which will actually give us some interesting stuff. We're not going to deal with any toroids in this class, simply because they're a little finicky to use for our purposes, and we don't have good ones sitting around. Really, a good use of a toroid, though, is if you wanted to keep a particle just kind of bound to a location, that's how you would kind of do it. But we're not going to really use toroids in this class for the AP Physics 2. Now, if you're doing the AP Physics C material, then you're going to need to know how to play with toroids in these equations a lot. And if you're doing the APC stuff, you better know how to work a solenoid in terms of the equations. They don't pop up a lot, but you don't want to be sideswiped with the free response question that pins you on a solenoid. But in your specific case, Liv, we're going to be doing a lab with this, and that's about as far as it goes. Okay? Kaylin, as to your question, north is negative and south is positive. My answer to that would be north is north and south is south. We use negative and positive for charges. Are you talking about like if you have a magnet though? If this is the north and this is the south side, like that's how the B fields work? Is that what you're talking about? I think. And technically they run through. That's annoying. Sorry. It is what it is. Yeah, we use positive and negative for charges, and then because we use that for charges, we use north-south for magnets. And because we use north-south for magnets, we have to use even weirder stuff for spin states. North is solenoids. North is negative and south is positive for solenoids. What do you mean by that? Can you explain what you mean by that? North is negative, south is positive for a solenoid. I'm not exactly sure I understand that statement. On a brighter note, my pen's working. What if I draw an eyeball? Kaylin, what do you mean by that? North is negative, south is positive Solenoids. I don't understand. I can tell you for a solenoid, you place your thumb in the direction you think the B field's going and you wrap your fingers and that's the way the current's going. Is that what you mean? You emailed a picture. Okay. Let's find it. Oh, okay. I see. Your question makes sense now. If we look at this sideways picture again, if the positive current is put into side B, what this means is that the current is flowing from B to A. So the current is wrapping, and this is sideways in the picture, it's wrapping around B to A. So the current's going into the page up top and out of the page on the bottom. So the current in this looks just like the current here, okay? It's going into the page up top and out of the page on the bottom because the current's going like this. In, out, in, out, in, out, in, out, in, out. And this is A, and this is B. So the current's going like that. If you're trying to figure out what direction the B field is acting, which is probably what this is asking you, if you curl your fingers in the direction of the current, your thumb points in the direction of the B field. So in our case here, since our current's going into the page up top, if we curl our fingers like that, we see that our thumb points left towards A. So our answer here is actually indeed what you have circled left. So great job on that. What do you guys, what should I wear tomorrow? I should probably wear a shirt and tie like always. What color shirt? Maybe I'll wear a blue shirt with a red tie. Freak my students out. Maybe I won't do that. That drawing just made everything make sense now. This one, this really cruddy one, wow. Boink, boink, smiley face. I'm a terrible drawer, but yeah. And this is actually traditionally how you draw a solenoid. It's actually something known as an inductor, which we'll get back to later on in the year. Okay, so I'm 50-50 on that. Liv says no, Kaylin says yes. Maybe I'll go with my white shirt with the polka dots on it. You know what I'm talking about? Or maybe I'll wear something so I can wear my white tie. I like the white tie. It's a cool tie. Black tie. Wear the sun outfit. Is that an orange shirt with a yellow tie? I think that's an orange shirt with a yellow tie. Is my orange shirt even clean? I don't even know if my orange shirt's clean. I think I wore my orange shirt this week. I don't think I can wear the sun outfit. I think this is off the table. Something spunky though. I don't know, I'll figure it out. Do you two have any other questions for me regarding Big Cheese or stuff? Yes. I think was that yes a question to more stuff. What are spunky ties? Purple shirt, green tie. No. Oh, that was shot down quickly. I only have one purple shirt. It's checkered. And I already did a green tie this week, remember? It was the orange shirt, green tie. That's what I wore. Maybe I wear all black. With a black tie. Like darkness. Okay, fine. I'll wear 6 ties tomorrow, going from my rainbow of colors. Okay, perfect. Maybe this can be like a very fat man. He's got a little... Oh, look, it's Hitler. How did I draw Hitler? Hitler, get off my computer. He's got feet. Cool. Okay. With that then, I'm gonna bail out. I need to figure out what I'm wearing tomorrow, and I need to figure out if this pen's ever actually going to work properly again, or if it's broken permanently. It seemed to work at the end there. If you have further questions, I'll answer them in class tomorrow. We're gonna have, let's see, a single period for the AP, and it's gonna be cut a little bit by our assembly, but we'll be fine. Okay, thanks for tuning in, everybody. This guy says bye. So, adios.